So, welcome, welcome, welcome. A big hello to everyone who's rolling in just now. Welcome to this live study session that's brought to you by Chegg. My name is Dr. Janita Pritchett Clay, or you can visit my page at Gen Chem with Dr. J, and I'm excited to be your virtual tutor for today. A little bit of background information about me as we wait for some people to join our live. I have been teaching general chemistry for close to 2 decades. I have a PhD in analytical chemistry and also run a nonprofit that introduces K through 12 students to science, technology, engineering, and math or STEM concepts through exciting hands-on activities. I actually launched my online platform, Gen Chem with Dr. J, to support students all around the world as they navigate their intro level chemistry courses. I'm excited to partner with Chegg tonight and every Thursday and this month to host these live office hours. For those of you who may be new to Chegg, they are here to make your academic journey a bit smoother. They have a ton of resources to help you get through school, like online study help, expert Q&A with step-by-step solutions, writing support, and a whole bunch more. If you're interested in checking out other classes that are available or tutoring hours, you can check that QR code that's in the top left corner so you can see the course schedule. Now, for those of you that have joined one of our lives before, welcome back. And for those of you that this is your first live joining, I hope this is not going to be your last. We like to have a lot of fun in these courses and make sure that you leave here with a bit more understanding than you came here with. So for tonight, we are going to be covering general chemistry. But again, if you're looking for other topics, check that QR code that's in the top left corner to see what other classes will be covered. So I'll be here each week on Thursdays to help you all navigate general chemistry topics. I have a few prepared questions, but I want to hear from you all. Definitely go ahead and start putting questions that you have or topics that you want to learn more about in the chat, and we'll be sure to answer as many of them as possible throughout tonight's live. And so as we wait a little bit for people to join us, I'm going to go ahead and kick things off with some of my pre-prepared questions to get us thinking about chemistry. As always, in any chemistry office hour, you want to make sure you have at least 2 things with you, maybe 3. First, you want to make sure you have a calculator with you. So I have a scientific calculator. Really, it doesn't matter what kind of calculator you have, as long as you can do exponents on it, that's going to help us get the job done. You also should have a periodic table somewhere nearby. We're going to reference this a lot throughout tonight's office hour. This will help us to identify where different elements are and pull information and learn how to read our periodic tables throughout our live. And then last but not least, grab a pencil and a piece of paper so you can take down notes, try some of the practice problems with me, and again, chime in through the comments, your questions or answers throughout tonight's session, okay? So let's go ahead and kick things off with one of our first prepared questions. Again, we want to hear from you. Please feel free to drop questions that you might have into the chat box. So last week when I was here, I ended up talking a little bit about how we can read the information from our periodic tables. And really what that helped us to understand is what information we can get from this shorthand summary, which is called an atomic symbol. And so on the bottom of the screen, you can see that an atomic symbol, when we're looking at describing an element, it has a couple pieces of information that we're going to point to. We have our element symbol, which is going to be the letter that's used in an abbreviated form to represent one of the elements. Now, sometimes the element symbol might have 1 letter or it might have 2, with that second letter always in lowercase. And so we'll pay attention to that as we're building out some of these atomic symbols. And then we also could have our mass number, which is found at the top of our atomic symbol. And then the atomic number, which we place at the bottom of our atomic symbol. Now, again, these different parts of your atomic symbol tell us so much information about the atoms that we might be looking at. Remember, our atoms, those are our building blocks that we use within chemistry. They're involved in all of our reactions. And so it's important for us to be able to pull information from those. And so our atomic symbol tells us information about what are called our subatomic particles. Remember, our subatomic particles include our protons, which are positive charge, our neutrons, which are neutral charge, and our electrons, which are negatively charged. And so when we look at an atomic symbol, our atomic number, that's going to be a whole number. And that whole number tells us how many protons the element has. And again, those protons are really important because they don't change in an atom. Okay, those are going to be consistent. And that's how we identify which element we're talking about. Now, our mass number, which is written as a whole number at the top, represents our protons plus our neutrons. So all of the mass, for all purposes, comes from those two subatomic particles. Now, the last subatomic particle, which are those electrons, they are negatively charged. Now, typically, if we have a neutral atom, meaning there's no charge for the atom, the protons will equal the electrons. But if we have an ion, which means we've either lost electrons or we've gained electrons, then that means that the electron number is going to change, where we're going to lose electrons to create our positive cations, or we gain electrons to create our negative anions, okay? And so again, remember, our protons define the element that we're talking about. And so with this information, we're able to make guesses or derive additional information based off of knowing one of the different parts of that atomic symbol. So for instance here, if we got the question of what element has an atomic number of 12, okay? So think back to what we just saw about what does the atomic number tell us? Well, it tells us the number of protons. So we know there's 12 protons here. But this is also how we identify our element. So go ahead, pull out your periodic table and see if you can find on your periodic table which element would have atomic number 12. Okay. And I do see we got a question about isotopic elements. We'll get a little bit into that in just a minute, what isotopes are. Okay, so atomic number 12, if we look on our periodic table, we would see that that goes to magnesium, right? We see in the top corner here how there's that 12. That 12 represents the number of protons that there are. And what was not asked here was the mass of this element. The mass number in this case would be 24. And so actually we can deal with the isotope question right now if we wanted to. And so if we drew an atomic symbol for this magnesium, we could say we have magnesium. And let's say that the atomic number is 12. So that goes on the bottom. And the mass number would be 24. Okay. And so if the mass number is 24, and we know that we have 12 protons here. Okay. So we have 12 protons in this number, in this atomic symbol. We would also have, let's say, if we try to figure out how many electrons we have. So again, our protons are positive. Because I'm thinking about this as a neutral element, that means that we would also have 12 electrons because our positive and negatives balance out. Our neutrons, we can actually figure out how many neutrons there are in this element. Because remember, your mass number is equal to your protons plus your neutrons. And so if that's the case, if we have 12 protons here, that means we would also have 12 neutrons. Now, an isotope represents an atom that has a different mass compared to what we would find naturally abundant, naturally occurring, right? And so these atoms can exist with a variety of different masses that are present. So let's think about how would the mass be impacted? Well, remember, we can't change the number of protons. That's fixed. So that means if we're saying the mass is going to change, that means the other subatomic particle, the neutrons, would be what has to change. And so if, for instance, we ended up having something that had 12 protons, 12 electrons, but now we're saying we had, I don't know, let's say 13 neutrons. Well, now it's still magnesium in this case because, again, the protons don't change. That's how we identify the element. But now the mass number would vary here because we have a different number of neutrons. And so we would end up having our protons plus our neutrons in this case, which would end up giving us a mass number of 25. Okay. And so hopefully that helps. Nathan 621 on TikTok for your how do we deal with isotopes in this scenario. Okay. Definitely feel free to put more questions in the comments as we keep working through some practice problems. Okay. All right. So let's try another one. Here we have a neutral atom contains 7 electrons. What is the atomic number of the corresponding element? All right, so take a moment. We got a lot of information here. Well, so it tells us that we have a neutral atom. So that's important. And it also tells us that we have 7 electrons. Well, what would the corresponding atomic number be? Remember, the atomic number is the same as which subatomic particle? It's not electrons. Instead, it is the protons, right? Your atomic number is equal to your protons. And so if this is telling us that we have a neutral atom, neutral means that our protons is equal to our electrons because that's a positive subatomic atom, and our negative subatomic atom are equal. They're canceling each other out. They're neutral. So if we have 7 electrons, that also means we have how many protons? How many protons do you think we have here? Yep, so I see Taybay on TikTok, 7 protons as well. Perfect. All right. So if we have 7 protons, that means that 7 is our atomic number. And from that, we would be able to say what element we're talking about. Which element would this be? If we're saying atomic number 7, which element would you say that is? Again, go to your periodic table, find your atomic number. Again, the atomic number is going to be the whole number that's found on your periodic table. That other number represents your mass. Okay. And so our atomic number here is 7. So that means we're talking about nitrogen. Great job, Destiny. S19 on TikTok. Perfect. Okay. Awesome. All right. So we're going to keep on moving on. And again, if you have questions about specific topics, please feel free to drop them into the chat. We'll try to answer as many of them as possible tonight. Okay. Perfect. All right. So I talked a little bit about ions in that last example. And so I wanted to just spend a little bit of time talking a little bit more about ions and help you to figure out whether or not something is going to become a positive ion or a negative ion. Okay. Again, remember, when we're looking at these atoms, the number of protons does not change. We could fluctuate the number of neutrons, and that's going to create our isotopes. And we can also fluctuate the number of electrons, and that's where we get our ions. So electrons are for ions, neutrons are for isotopes, okay? Now, because electrons are negatively charged, if we add more or we take away them, that's going to impact the overall charge of that atom. And so anytime when we're having a chemical reaction happen, if an atom loses or gains an electron, that's when it becomes an ion, okay? And so oftentimes our metals, and just to help you remember your periodic table, okay, this is what our periodic table looks like. We got that little step that's going down here. This whole area on the left-hand side, these are our metals, okay? And this area up here are our nonmetals. Okay. And then the step, those are our semimetals. Okay. And so typically when we're dealing with ions, your metals, they're going to lose electrons. Okay. And so anything that's on that left side of the periodic table, they're going to be the ones that are going to kick out that electron. Okay. Or electrons to form positively charged cations. The way I like to remember this, most people like cats. That makes them happy. So cations have a positive charge, okay? And so this is happening when we lose electrons. And your negative ions are called anions. The way I like to remember that, anion, if you look at how it's spelled, it kind of looks like onions. Onions, if you eat them, I love them, but they can make your breath smell bad. Bad is negative, so anions are negative. Run with it if it works for you, okay? But for your anions, they're going to be gaining electrons, okay? And in either case, they're going to be trying to either kick out all the electrons that they have to get down to 0 electrons in their outermost shell, that valence shell, or they're going to gain enough electrons to get up to 8, okay? So that they have a full valence shell, okay? And so to figure out the valence number, how many valence electrons an element has, we're going to look at what's called the group number, which is basically corresponding to the column that it's in, okay? And now this trick will work for what are called our main group elements, which are our first 2 columns on the left-hand side, and then those last 6 on the right-hand side. So each group basically tells you how many electrons are in their valence shell. We won't worry about this transition section right here. Don't worry about that section right now for this process. But if you're in group 1 or column 1, that means you have 1 electron. And so if you have 1 electron, we want to kick that 1 electron out so that we can get a positive 1 charge because I lost 1 negative electron. Group 2, which is column 2, has 2 valence electrons. And so we want to kick those 2 out. And now we have not a positive 1 charge, but a positive 2 charge. Okay, so it's just going to build up. Group 3, now if we jump over to the other side, past those transition elements, has 3 valence electrons. And so we kick those 3 out. Now we have a positive 3 charge, okay? Now on the flip side, go all the way to like group 7, where your fluorine, chlorine, bromine are. Well, they have 7 electrons. Now it's a lot more difficult to kick those 7 out versus getting 1 more to come over, okay? And so now, instead of kicking out all 7, it's going to gain 1 electron so it can have a full octet, a full valence shell. And so because it took on 1 negative electron, it's going to have a negative 1 charge. Group 6, again, difficult to kick those 6 electrons out. It's easier to go gain the 2. All right, so it's going to gain 2 negative electrons. It will take on a negative 2 charge. And then group 5, again, hard to kick the 5 out, easier to get the 3 to come over, gets a negative 3. Now, this group 4 could actually, depending on who it is bonding with or reacting with, it could go either way, positive 4 or negative 4. And notice group 8, the last group, which is our noble gases, they actually don't want to do any of this. They're good. They have their 8 electrons there. They don't want to lose. They don't want to gain. So those, they often tend not to want to be involved in reactions. Okay. So just giving that a little bit of background for you. So let's talk about how we assign our ion charge. Okay. So I have some examples for you here. And we're going to work through a few and see if you can predict the charge. Okay. So the way you're going to do this, find the element on the periodic table, figure out which column or group it's in. Based off of that, we'll assign the charge. Okay, so let's take aluminum first. So for aluminum, find the group that it's in, and I want you all to tell me, what charge do you think aluminum has? So would aluminum become a cation or an anion? And if so, either one, what charge would it have? Okay, I see some questions about scientific notation. I will definitely handle some of that. I see someone shouting out the halogens. Yep, group 7. All right, so looking at aluminum, aluminum is in group 3. So again, if I'm in group 3, is it easier for me to kick the 3 out or go try to convince 5 more to come on over? Okay, we're either trying to get down to 0 or get up to 8. So it's easier to kick the 3 out. So if I lose my 3 electrons, what charge would aluminum now have? Would it be positive 1, positive 2, negative 1, negative 2, positive 3, negative 3? What do you all think? Okay. What you should be saying, if it had 3, I'm going to kick those 3 out. I lose 3 negative electrons. So that means aluminum is going to become positive 3. Okay. All right. We'll try another one. Let's try like sulfur. Sulfur, find it. It's in group 6. So now I have 6 valence electrons. Do I want to kick those 6 out or keep the 6 and go get 2 more to come over? Okay, it's a lot easier for it to get those extra electrons to come on over. And so our sulfur is going to gain 2 more electrons to get up to 8. So that means it would become a -2 charge. Okay. So in aluminum's case, that is considered to be a cation because it's a positive charge. In sulfur's case, that would be an anion because it's a negative charge. Okay. We'll do one more. We'll try bromine. So bromine, to Yagi TikTok, is one of our halogens, right? So as a halogen, group 7, it has 7 valence electrons. So again, those 7, it's kind of hard to kick all of them out. It's a lot easier to just try to get 1 more to come on over. And so if we bring on a negative electron, 1 negative electron, bromine will end up having what charge as an ion? Okay, I gain 1 negative electron. And so it will become more negative. So it's actually going to have a -1 charge. When it's -1 or +1, you don't have to put the -1. You can just put the negative symbol, and the 1 is implied. Okay, and so that would be our another anion. Okay. And similarly, when we're writing atomic symbols, we can show that ion charge in our atomic symbol. Okay, so let's try this out with our barium example. All right, so we want to write the atomic symbol for neutral barium and the barium cation. Okay, so remember your atomic symbol has 3 parts. It has the element symbol, it has the mass number, and it has the atomic number. Okay, so if we can look on our periodic tables, we see barium is a group 2 metal. Okay, its symbol is Ba. If I look on the periodic table, it has 56 as its atomic number, so that's going to go on the bottom. And 137 would go on the top as a mass number. Now, because it's neutral, we don't put any symbol on there, no charge on there. But if we want to make the barium cation, well, what's going to change? Well, it's still barium, so the symbol doesn't change, right? And because it's still barium, we also know that the protons don't change, which means the atomic mass stays the same. Well, it's a cation. Remember, the cation does not change our neutrons or the protons, so the mass number will stay the same. But what does change are the number of electrons that are present. If it's a cation, that means it is losing its electrons, and so it will kick out 2 electrons and take on a +2 charge. Okay, so that would be how we would write our atomic symbol. Okay, so definitely try that chlorine example out. We'll come back to it a little later if we have some time, but I do want to make sure I get to answer Jasmine's question about unit conversion. Okay, all right. So I'm just going to go ahead and advance to a blank screen here. All right. So Jasmine, you say you're struggling a bit with the scientific notation and the unit conversion. Jasmine on TikTok. Okay, so let's just go over that unit conversion, how we should be setting things up, and then talking about how you should be putting in your calculator. Because what I found, a lot of times students struggle with how to put it in the calculator properly and not so much on the where things go, okay? And so remember, when we're doing unit conversion, we want to use this given and find format. And so typically you're going to have some problem and you're given some information. Let's say you have, I don't know, 2.5 times 10 to the second milligrams of something. Okay. And we want to solve for something else. Okay. And so I could say, convert 2.5 times 10 to the second milligrams to grams. Okay. And so the given and find format, the way we set this up when you're doing any unit conversion, we will create a little conversion bracket. And on the bottom, we're going to put the units that are aligned with our given, because we want this to cancel out. And we'll put the units for what we're solving for on the top. Okay. And when we're plugging in the calculator, anything that's on the top, we're going to hit the multiplication symbol for. And anything that's on the bottom, we're going to hit the division symbol for. Okay. Now, occasionally you might have something that's not able to be done in a one-step problem. So you might have to do multiple of these given, find conversion brackets. And we can go through an example of that shortly. Okay. So what you'll have to look at is, okay, whatever I'm given this 2.5 times 10 to the second milligrams, and I want to find how many grams. So you should ask yourself, well, is this a one-step problem? Do I know how to go from milligrams to grams in one step? And you should say yes. We have a conversion factor that says 1 gram is equal to 1 times 10 to the third milligrams. Okay. And so because I know that direct conversion from one to the other, I can put one conversion setup there. And now we want to think about, where do we put our units? On the bottom, because I'm starting in milligrams, I would put milligrams on the bottom. I always like to put the units in first before I put the numbers in, because I want to make sure that mathematically I'm setting things up properly. So if I put milligrams on the bottom, I could then put grams on the top. Okay. And now this conversion factor that we know, hopefully you've memorized, or you might, depending on how your class is set up, you might get that as a resource. But bank on you probably need to memorize it. Now we can plug that into this conversion factor. And so I can put 1 on the top with the grams, and 1 times 10 to the third milligrams on the bottom. So that's basically saying there's 1,000 of these milligrams in a gram. Okay. And so now when it comes to typing this in your calculator, this is where it's going to be dependent on what kind of calculator you have, Jasmine. All right. And so most calculators have either like a EE button or like a EXP button, or maybe even a X times 10 button. So it's really going to depend on how your calculator is, but you need to figure out where your exponent button is. And remember that when you hit that exponent button or the EE button, that represents times 10 raised to. So you don't have to put this part into the calculator. When you're typing it in, you typically are just typing in like 2.5, then you'll hit that EE or EXP button, and then the exponent. So the 2. So on my screen, I now see 2.5 E2. But the E, that represents times 10 raised to. So you don't have to do that. If you can't find that EE or EXP button on your calculator, you might also have, you might be typing in times 10 caret symbol, which is fine, but you'll need to make sure you put all of this in parentheses so that it all stays together. And that's really, really important when you do the division symbol, the division step, because if you don't put the parentheses around it, then it separates it. And basically it would just divide by 1 and then bring the 10 to the third, it would multiply instead of dividing by the whole thing. Okay. So it's kind of calculator specific. Nonetheless, get it typed in. So it says 2.5, hopefully E2. Now you're going to times by 1 and then divide it by 1E 10 to the 3 or 1E3. And so when I put that in, I end up getting 0.25 grams as my answer. Okay. All right. And I'll do one more conversion problem just so you can see what we would do if this was like not as simple as a one-step problem. Okay. So what if we had like 3.24, and I'm giving you some that has exponents in it, 10 to the negative, let's do, let's say -3. I'm just making up numbers at this point. 3.24 times 10 to the -3. And let's say that this is kilometers. And we wanted to convert this to, let's say, centimeters. Okay. So how many, if we have 3.24 times 10 to the -3 kilometers, and we wanted to get to centimeters. Again, the main thing you want to note here is like, how do we know how many steps would this take? And so when I look at the kilometers versus centimeters, I know that I have two prefixes there. I have kilo and centi there. And so that's normally an indication that this is going to be at least 2 steps, because I might not know a direct conversion from kilometers to centimeters, but I do know a conversion from kilometers to meters, and then also from meters to centimeters, right? And so I know that 1 kilometer is equal to 10 to the 3rd meters. So there's 1,000 meters in a kilometer. And I also know that 1 meter is equal to 10 to the 2nd centimeters. And so now knowing those conversions, again, hopefully you have those memorized or you'll have them as a resource. I know that this is going to take 2 steps because I have to go from kilometers to meters first and then meters to centimeters. Okay. And so when I'm plugging things in, I'm still going to put my units. I want to get rid of kilometers. So in this first bracket, I'm going to put kilometers on the bottom because I want to get rid of it. Again, don't worry about getting the numbers in just yet. Get the units in first. Let that drive the way. So I'm going to put kilometers on the bottom and I'll put meters on the top. That's going to allow me to cancel out my meters. And if I was, or excuse me, my kilometers, if I was done with the problem right here, I would have meters left. But I'm not done. I need to get to centimeters. And so now I would put meters on the bottom and now centimeters on the top. Okay. Now I'm going to plug in those units directly, the information. So I know 1 kilometer is 1 times 10 to the 3rd, or you could just write 10 to the 3rd meters. And I know 1 meter is 1 times 10 to the 2nd centimeters. Okay. And we'll get ready to plug those in. All right. So go ahead and type in, again, 3.24, find that EE button or EXP button, EE, -3. Again, I don't need to do EE times 10. The EE represents that. Now I'm going to be multiplying for anything I see on the top. So times 1 EE3 times 1 EE2. Then you would divide by 1, because those are both on the bottom. And so what that ends up getting is 324 centimeters. Okay. Hopefully that worked out for you all. I see ABC on TikTok said it makes so much sense now. I'm glad it worked for you. And also Motivated Man, Knowledge is Power on TikTok. Thank you. I'm glad that you enjoyed it. All right. All right, I see another question from Jasmine about speed, and we want to convert from 72 miles per hour, and we want to get that to feet per second. Okay, so let's try that one out. Okay, so let me clear out my space here. We're still going to be using that given and find format. Okay. And we're probably going to need to look up a unit for ourselves just in case if we don't know it, but that's what Dr. Google is for. It helps us out sometimes if we need it. All right. Sorry, I just cleared my screen out real quick. All right. So Jasmine from TikTok, you said we have 72 miles, and I'm going to actually just spell it out, miles per hour. And we want to get to feet per second. Okay. So now this one, we actually have two sets of conversions that we have going on here. Okay. And so what I encourage you to do, and actually I'm going to write this a little bit smaller so I have a little bit more space to work with, is to focus on the top and the bottom separately as you are solving this problem. Okay. So we want to end up in feet per second. Okay. All right. So act like you don't even see the bottom part right now. Act like it was just like we're trying to go from miles to feet. Okay. And so the question we would have to ask ourselves, do we know a direct conversion between miles and feet? Basically saying how many feet are in a mile, right? And if my memory serves me correctly, I am going to have to pull this up from Dr. Google, but I believe there's 5,260 feet in 1 mile. Let's just confirm that. How many feet in a mile? 5,280 feet. So, yep. Okay. So 1 mile is equal to 5,280 feet. Okay. So that's one part that we're going to need to deal with. Okay. And so because we know that that's a direct conversion, that's going to require at least one conversion step. Okay. And then the other part we have to deal with, we will eventually have to deal with the bottom, and that's dealing with hours to seconds. Okay. And so if we looked at hours, now you might say, well, I don't really know off the top of my head how many seconds are in an hour. Of course, we could go to Dr. Google one more time and pull that up, but we're actually going to do a little bit more math here. We should know maybe not how many seconds are in an hour, but hopefully we know how many minutes are in an hour. Right. And we know that in 1 hour, there are 60 minutes. And then we also know how many seconds are in a minute. So we could say 1 minute is equal to 60 seconds. Okay. And so those are the 3 conversions that we're going to have to weave together. Okay. Focus on one part at a time. So now that we have those conversions, this tells me this should be doable in 3 conversion setups. Okay, let's test that out and see if we get that. Okay, focus on just the miles. Act like you don't see the hours. If I'm starting in miles, I need to put miles on the top or the bottom of the first conversion if I want to get rid of it. Okay, would that go on the top or the bottom? Remember, put your units, let the units drive us. We want to get rid of miles, so we're going to put miles on the bottom. And on the top, we will put feet. Okay, because that's the conversion that we know. Okay. And if we filled that information in, we would say we have 1 mile is equal to 5,280 feet. Okay, we're just translating what we know. Now, at that point, if we stopped, we would be able to cancel out our miles, but we would not have feet per second. We would have feet per hour right now. Okay. And so now our goal is to focus on getting the bottom part, the hours, to match what we're trying to solve for. And so if hours are on the bottom and we want to cancel that out, that means we're going to put hours on the top in the next bracket so that it can cancel out. So we're going to put hours on the top, and we're first going to say how many minutes there are. So we could say 1 hour is the same as 60 minutes. And so now hours have canceled. Now we'd have feet per minute, but we want feet per second. And so now we want minutes to cancel out. So we'd put minutes on the top and seconds on the bottom. And so that would be 1 minute is 60 seconds. Okay, you could have condensed that step, the last two steps, into one and said 1 hour is equal to 3,600 seconds off the bat. But if you're not familiar with that, that's okay. We can do it step by step. Okay, so now when we plug it in our calculators, multiply by anything that's on the top and anything that's on the bottom, we'll hit the division symbol. So you should be doing 72 times 5,280 times 1 times 1. Then we're going to divide by 1, divided by 60, divided by 60. So I always say multiply across the top, then divide by the bottom. So multiply, 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 divide, divide, divide. Instead of going up, down, it's just easier. Okay. And so when I plug that in, I would love to hear what do you all get. When I plug this in, let me know if you got an answer. What you should get when you plug this in, at least what I got 105.6 feet, because my minutes are gone, per second. And for those that were here last week, we talked a little about sig figs. Right now, this would technically not have the appropriate number of sig figs based off of what we started with. We started with 72, which means there's only 2 sig figs shown. And so we would need to show this answer showing only 2 sig figs as well. And so that means we would have to stop here. So we would round up. And I would probably write this in scientific notation. So rounding up, that would give us 1.1 times 10 to the 2 feet per second. If we were given it as 72, it might have been 72.0, and then that would allow us to have 3 sig figs. But because we started with only 2 sig figs, we technically should be showing 2 sig figs at the end. Hopefully, Jasmine, did you get the answer correct from TikTok? Hopefully that helped out with that conversion. And I always like to check my math. 5280 divided by 60, divided by 60. And yep, I still got the same answer. Okay, perfect. All right, other questions, feel free to put them in the chat. Again, as we are going through this, if you have other questions or want to see other topics, Chegg is hosting a number of different courses. You can just scan that QR code in the top left corner to see the full schedule. Okay. All right. I'm going to keep it moving to a couple more problems. All right. So we're going to switch gears. All right. I see OMG. Thank you, Dr. J. Awesome, Jasmine. So glad that you were able to solve that. All right. We're going to switch gears a little bit. Okay. And again, if you want me to stay with doing unit conversion, let me know. But I know we have a lot of people in a lot of classes, so I want to cover a few different topics for y'all. So I wanted to get into naming of elements, naming of compounds. Occasionally, you're going to have to name different compounds. That's a huge part in chemistry. And so it's important to know how to do the naming of compounds. And so we're going to focus on 2 different naming formats. One format is for when we're dealing with what are called molecular compounds. And so a molecular compound is a compound that consists of no metals present. Okay, typically it's 2 nonmetals. And we'll also learn how to name ionic compounds. And ionic compounds typically, for the most part, will have a metal present with a few exceptions. Okay, so there's going to be 2 main naming schemes that you're going to learn about in this class. Okay, so when we're dealing with molecular compounds, again, molecular, primarily 2 nonmetals. Again, I'm going to quickly draw our periodic table schematic. Okay, remember, these are our metals, these are our nonmetals, and then these are our semimetals. So when you have a compound, and so compound means there's two or more elements that have come together to form one thing. Okay. Our naming system is very much set in stone. Okay. And so when we're naming things, we're going to follow this format down here on the bottom. We're going to be indicating how many of each element are present by using these prefixes that are available. Okay. And so most of the prefixes you've probably have heard before, like mono, di, tri, penta, hexa, hepta, should be very reminiscent of like a geometry class, maybe if you've taken them before. But that prefix is describing how many of each of that atom are present. Okay. And so when we have two nonmetals, we'll have a prefix first that describes the first element. Okay. And then we use another prefix to describe the second element. But now we take the base of that element and we drop the ending and we're going to add ide, IDE. And so when you see that ide, like chloride versus chlorine, the ide indicates that you're dealing with a compound. So like sodium chloride, well, that wasn't the best example because that's an ionic compound. That's an example nonetheless. It's a compound. So the ide is what you'll see whenever you deal with compounds. Okay. Now, important when we're dealing with the prefixes in this first position only, you can never put mono here. Okay, you can put any other prefix there, di, tri, tetra, penta, hexa, all of them. You can put mono here in the second prefix. Okay, but you don't put it in the first prefix. And so many people know that this compound, CO, you know that as it's a gas that we don't really want to breathe in. That would be carbon monoxide. We don't say monocarbon monoxide because that mono in the front would be a bit redundant. And so I give that example because we never use mono in that first position when we're naming something. Okay. And so let's try naming a few of these different compounds. Again, here, I'll just quickly draw our schematic for us. So we have prefix first, then the element name, then prefix, and then the element plus IDE. Okay. All right. So we have NO2. NO2. Go ahead and give me some guesses on how we would name that. And so what you should be processing here is that, okay, there is no metal present, both nitrogen and oxygen. That's a group 5 and group 6 element. And so we're going to name them. Remember, if you only have one of the first element, we never put that mono prefix before it. And then we would name it as well. Okay, so go ahead and definitely drop your guesses on how to name that first one. And I see Pacha Batala, loving our lectures from India. I'm so glad that you're joining us from India. I'm glad that this is helpful to you. Okay. So try naming NO2. How would you all name that one? NO2. Okay. And so we see that we only have one nitrogen. And so the prefix we would want to use is mono, but mono is never used in that first prefix. So we would say nitrogen, just nitrogen first. And then we see we have oxygen, and we have two of them. And so two, the prefix we would use is di. Okay. Maddie, you're so close. Nitrite. I see where you're going. And I'll talk about, I know where you got that from. Okay. We're going to talk about that in just a second. This is not quite nitrite, although that tells me you've been learning about your polyatomic ions. All right. So here we would say nitrogen di, and then we would say oxide because it's the base of that element plus the IDE ending. Okay. Now, so this would be the name, nitrogen dioxide. But Maddie from TikTok, you made a great guess of saying nitrite. Okay. So nitrite is a special thing. Okay, so that is what's called a polyatomic ion. Okay, and so a polyatomic ion, if you break that word down, poly means many, atomic, so many atoms, ion, remember we just learned a few slides ago, has a charge. So this is many atoms together with a charge. Okay, notice up here there's no charge listed, right? So it's just NO2. So that is a compound without a charge. It's neutral. This is considered a molecular compound. The nitrite, which you're thinking about, that is NO2 with a negative charge. So NO2 minus. Fun fact, when I was doing my PhD, I spent a lot of time measuring nitrite in the eye because that is a sign of damage that could be happening at the optic nerve head. And so very great guess, but the difference between NO2 minus, that minus sign there, that's an ion, that's a group of atoms that are stuck together, okay? All right, so hopefully that helps, Maddie. I see some other guesses coming through from Manny and Tridu from TikTok for the next one for PCl5. And both of you all saying phosphorus pentachloride, absolutely perfect. So phosphorus, penta, that's good. The penta means 5, then chloride, IDE, okay? Perfect. All right, and so then let's try the last I2F7. We want to get our last two. I see the answer has come through. So almost. All right, very close. The first part is perfect. All right, so I see diiodine septafluoride. Okay, but it's actually going to be diiodine, and so that's for I2. Right, there's two iodines. The prefix for 7 is actually hepta. So it's a little bit different, but it's heptafluoride. And so our prefixes, 1 is mono, 2 is di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, N-O-N-A, and then 10 deca, okay? So very, very close. So including mono is redundant in this case here, JTHE3 on TikTok. So here, notice in these cases here, we didn't say mono nitrogen or mono phosphorus, that it is redundant in that position. So we never use mono in the first position. But in the second position, so like I said, if we did carbon monoxide, you can have the mono prefix there, okay? Okay. And it's a reasonable guess, Tridu, of septa. And I think septa can be a prefix that's used to represent 7 other scenarios, but here hepta will be your prefix that you're going to be used. Okay. I'm seeing, why can't I switch it to 1.5x? I'm not sure what that refers to. If you want to give me a little bit more context, Murat, that would help me out. Okay. All right, we got just a couple more minutes. I think I can probably do like one more question before we get ready to round out for tonight. And actually, let's just keep on this theme. And so let's see if we can go the other way. So we just spent the last slide going from the formula to the name. Well, now let's try going from the name to the formula. Okay, so based off what we see, dinitrogen, tetraoxide. Okay, what would that formula end up being? Dinitrogen, tetraoxide. What do you all think that first formula would be? Any guesses? Because again, remember the di That's telling me how many of nitrogens we have. Tetra is telling me how many of the oxygens we have. Ah, perfect. Tree do on TikTok. That is N2O4. Perfect. All right, good. All right, let's try sulfur hexafluoride. Sulfur hexafluoride. Okay. Now again, notice no prefix here, so that tells us something without even telling us something. And then we got hexafluoride. What would this compound be? Okay, drop your guesses in the chat. Okay, sulfur hexafluoride. Any guesses? Any guesses? Sulfur hexafluoride. So in this case, we have no prefix here, so that tells us that it is just only one present. And I see SF6 perfect coming through in the chat. SF6. Hexa telling us we have 6 fluorines. Okay. All right. Last one to wrap up. We have diarsenic trisulfide. Okay. And this one's it's kind of a trick, but not really. We'll see if you all can get this right. Okay. Diarsenic trisulfide. Ah, Treedo, you did not fall for the trick. A lot of people, when they see that diarsenic, they're like, arsenic, AR. The AR is actually argon. So yes, arsenic is AS, and we have 2 of them. And then sulfide, and we have 3 of them. Okay, perfect. Okay. And I see in the problem before from Absolutely Mr. Fashion, you have SH5 for the one above, I think. And I think you might have been trying to get to SF6 to solve the one above. Okay. All right. And yeah, for arsenic, we want the symbol of AS. And so this will be, if you have your periodic table, you want to make sure that you're finding where arsenic is and using that as your symbol. So arsenic is here. It's kind of hard to see. It's number 33 on your periodic table. And so that's what we'll be using. SR that you just put in, that is actually strontium. So that would be different than arsenic as well. Okay. And so we are starting to wind down for today's activity. We can definitely pick this up again next week with some more naming. We can also get into unit conversion, whatever you all you desire to learn more about. And so I do want to remind you all that there are live sessions happening all throughout the week. That's QR code that's in the top left corner takes you to the course schedule. I highly recommend that you check it out so that you can get additional help. I'll be back next Thursday at the same time, 8:30 p.m. Eastern time or 5:30 p.m. Pacific time. So you can join us here on live. And then also, I just want to thank you all. Thank you all for all your questions, for engaging throughout today's content. I hope that you all enjoyed learning a little bit today. I hope that you are ready for whatever test or homework that you have coming up about. I really appreciate it. I do encourage you all to check out chegg.com if you haven't already done so. Again, a ton of resources that are available for you, 24/7 support for some of your toughest subjects. Also, make sure that you follow Chegg here on TikTok, YouTube, Instagram, Twitch for more content like this. And just remember, we're here again next week. So until next time, thank you all so much for joining, and I look forward to seeing you all again soon. And again, Gen Chem with Dr. J. Make sure you follow me as well. Have a great day, y'all.